talk about what exactly we would use or what we could use the standard normal distribution for. As an example, just to kind of set up the stage here, let's consider you doing a full triathlon, okay? And according to someone 5th period, an average time for a triathlon is somewhere around 12 hours, okay? So let's say 1 year you compete and the mean time is 12 hours and the standard deviation of all the times of the runners is 1 hour, okay? And let's say it takes you 2 hours, okay? Your time is 2 hours. Let's say you run the next year, okay? And let's say that because of the weather, people are going slower. And let's say that this year, the mean was 14 hours. And the standard deviation was 1.5. Okay? And this year, your time was, wait, your time here, 2 hours. Your time, yeah, it was really impressive. Your time was 14 hours. I was thinking it was 2 more than what the mean was. Your time here was also 2 hours higher than the mean. Okay? And the question is, relative to how everyone performed, which year did you do better?
You didn't
okay. Okay? The idea here is, why would you say we did better the second year?
Because so in the first one, you're 2 standard deviations higher than the mean, and in the second one, you're less than 2. You're more than 1 less than 2 standard deviations above the mean.
Okay. So here, that 14 hours is 2 standard deviations above the mean. Okay. So if you were looking at your time relative to everybody else, okay, here's our mean, 1 standard deviation, 2 standard deviations, okay, you're at like the bottom 2.5%, okay?
Pretty bad.
You'd be at the slowest 2.5%, right? Because 2 standard deviations contains 95% of the data, and then there's another 2.5% on either end, okay? So you performed at the slowest 2.5% of everyone who raced, which is still impressive because if you could do anything if you could move period for 14 hours straight, you're doing a lot better than I would, okay? All right, so just finishing these races is an accomplishment. But here you have 16 hours, okay? And even though your time is higher, notice that, if here is our mean, 1 standard deviation would be at 15.5. The second standard deviation would be at 18 hours, okay? So the fact that you're at 16 hours, you're like right there. We could actually use the normal PDF, if we wanted, to figure out what percentile you were at. If we went from 0 up to 16 hours, we could also use the normal PDF to figure that part out at 97.5 about. Okay? So you're right, in this second year, you actually performed better compared to the rest of the field. Okay? In fact, instead of being in the, approximately, the 90, we'll round up to 98th percentile as far as being slow. Okay, here, remember one standard deviation away from the mean, that's 34%. So you're up to 84%, a little bit past that, you're somewhere probably around 88%. Okay? And that's just a guess, but all right, but you can see there's some significant improvement in your performance overall. And what this allows us to do, what we just did is, you know, rather than look at it just in terms of the number of hours, this allows us to take into account the fact that, hey, there was another variable at play here. The weather impacted the entire race, and it impacted everybody. Okay? So in this case, we're at the mean plus, that would have been plus 1 1/3 standard deviations. Here we were at the mean plus 2 standard deviations, so we were doing a lot better this time. Okay? Now, looking at, guys, please quit, all right? Take it down. Looking at it in terms of standard deviations is actually what the standard normal distribution does. It translates everything into a situation where we have a mean of 0 and a standard deviation of 1. If you remember our notation, x is distributed normally with a given mean and variance. Here, another name for the standard normal distribution is the z-distribution because we use z,
the z-scores
and z-scores, okay? And those z's are going to also be distributed normally.
So if you have a z-score of 2, then you're 2 standard deviations away.
Exactly. Here, the z-score would equal 2. Here, the z-score would be 1 1/3. Okay? Now, what I want to do here real quick is look at a little video that kind of sums all this up and derives some of this. So pay close attention. He does talk a little fast, and instead of Z, he says Z because he's Canadian. All right?
That's a thing.
Yeah, Canadians and Brits usually say Z. Yeah. So, but anyways, he does talk somewhat quickly. You don't need to try to write a bunch of stuff down here. We're going to look at it, but I want you to see it kind of run through in a pretty succinct way here, okay? So, let's look at this. There we go.
Variables. Suppose x is a normally distributed random variable with mean, mu, and standard deviation sigma, which we sometimes write notation-wise as x is distributed normally with a mean of mu and a variance of sigma squared. This is not universal notation, but it is pretty standard. X is distributed normally with a mean of mu, and the second term is the variance, sigma squared. The standard deviation of sigma, of course. Now suppose we want to standardize this. In other words, turn it into something that has a standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. How would we do that? Well, let's think. X has a mean of mu. So if we go x minus mu, then this quantity is going to have a mean of 0. And if we divide by sigma, then this whole quantity is going to have a standard deviation of 1. This is a basic linear transformation, and we forced this quantity to have a mean of 0 and a standard deviation of 1. And so I'm going to call this z. If we let z equal x minus mu over sigma, then this random variable z has the standard normal distribution. And so I'm going to write it as SND the same as I'm writing, or in other words, z is distributed normally with a mean of 0 and a variance of 1. equivalently a standard deviation of 1. Suppose the height of adult American males is approximately normally distributed with a mean of 176.3 centimeters and a standard deviation of 7.1 centimeters. Well, that distribution looks something like this. Normal distribution right here in the middle is the mean and the median, because the mean and median are the same for the normal distribution. That's 176.3, and we have a standard deviation of 7.1 centimeters. And so we can use this distribution to do some probability calculations. For example, what is the probability a randomly selected adult American male is taller than 180.0 centimeters? Let's let the random variable x represent this height of this randomly selected adult American male. And we want the probability that x takes on a value that is greater than 180.0 centimeters. Well, if we draw out our distribution of heights with 176.3 in the middle, and 180.0 is over here somewhere, and we want the area to the right. That's going to give us the probability that x is greater than 180. Well, let's see. What if I did this? This is equal to the probability x minus mu. I'm going to subtract mu and divide by sigma on both sides. I'm allowed to do that. Sigma is positive, so we're dividing by positive values, so we don't have to worry about anything flipping. This is correct. This is fine. But I also know that z is equal to x minus mu over sigma. And so this is z. So this thing is the probability that z is greater than 180.0, and I'm going to put in the actual value of the mean now, and divide by the standard deviation. And this works out to the probability that z is greater than 0.521. And that is simply the area under our standard normal curve out to the right of 0.521. And we can use a computer or we can use our standard normal table, and I'm going to let you do that and verify for yourself that this is actually equal to 0.301.
All right, he mentioned a standard normal table. I want to actually show you that here. Okay, so he has z as 0.521. All right, if we go here and we look at a standard normal table, okay, z is 0.521. Now look at how this table works. You have the whole number in the tenths place right here. The hundredths place is the different columns. So if I'm doing 0.521, here's 0.5. This doesn't go to the thousandths, so 0.52 is 0.6985. Okay? 0.6985. All right, because this is 0.52. All right, now, notice he got a little different percentage. He got 0.3015. That's because this table always gives us the area below that z value. Okay? So the area below 0.52 is 0.6985, which means the area above is 1 minus that. Okay? That's how we got this 0.301. Does that make sense? All right.
I don't understand why he was allowed to subtract mu and divide by sigma to the x.
Here?
Yeah.
Well, basically, this is an inequality, right? And you're allowed to do algebra on an inequality as long as you're fair.
Well, why? How is he allowed to subtract? I understand how he did it on the left side, but like, how
Here?
did he, yeah, how did he know that to figure out what the probability was? You have to subtract the mean and divide by the standard deviation.
Well, he was just being fair to both sides of his inequality. He had to subtract the mean from both sides.
So why did he say? Why did he say that z had to be greater than it? Because isn't z?
Well, because that's how z is defined. Z is x minus the mean divided by the standard deviation. And once he did this, he recognized, hey, that equals z, so he plugged it in. Okay? And then when he plugged in the values from this specific problem, he got the 0.521. Okay? Well, that's the thing. We're going to make all of these work this way. Okay?
So literally.
We're forcing a normal distribution that we're given, we're forcing it into the standard normal distribution by subtracting the mean and dividing by the standard deviation. Okay? Let's look at another one here.
What is the probability a randomly selected adult American male has a height between 170.0 and 180.0 centimeters? We want the probability that x lies between 180.0 and 170.0 centimeters. And that is, of course, the area under the curve between 170.0, which is over here somewhere, and 180.0. Over there somewhere. That's what we want to find. And we're going to convert this, we're going to standardize this, so we can look it up in the standard normal table if need be. And so I'm going to skip a step here, and I am just going to go straight to subtracting the mean, which is 176.3 centimeters, and dividing by the standard deviation. And now I can call that z, because I'm standardizing this. So 180.0 minus 176.3, again divide by the standard deviation, and we've converted from x to z. So this is the probability that z lies between minus 0.887 and 0.521. And this is our area under our standard normal curve between minus 0.887 and 0.521. That is the probability that we see. And I'm going to let you throw that into a computer, use the standard normal table to find that that area is 0.511, which means that this probability is 0.511.
That doesn't make sense.
Here's a different type of problem. What is the 90th percentile of the height of American males? Well, here's my distribution of the height of American males, and here's 176.3 in the middle. And the value of the variable, the value here that yields an area to the left of 0.90 is the 90th percentile. That's what I want to find. So one way we have of doing this is we can say, all right, let's find the 90th percentile for the standard normal distribution. So we'll find the 90th percentile for the standard normal distribution, and to 2 decimal places, that's 1.28.
Okay, where did he get that from? Let's take a look back at our standard normal table. If you look through all these percentages, you can see here's 0.8889, here's 0.898, 0.8997, right here, okay? 0.8997. And if you look at what value that gives us, that's 1.28, all right? 1.28 for Z. Okay? That's where he got that number from. Okay? Now he's going to convert that, kind of undoing that process of x minus mu over sigma to figure out what x value has this Z value. Okay?
I'm going to let you verify that for yourselves using a computer or a standard normal table. So the 90th percentile of the standard normal distribution is 1.28. And we also know that z is equal to x minus mu over sigma, which implies, if we rework that x is equal to mu plus sigma z. So if my 90th percentile of the standard normal distribution is 1.28, the 90th percentile of the distribution of x is the mean plus the standard deviation times the 90th percentile of z. This works out to 185.4 centimeters. So the 90th percentile of the height of American males is approximately 185.4 centimeters.
All right. So we will be doing a little bit of all of that.
Can you go back to the one where x is in the middle?
We are going to do some. We'll see. You'll see it. Okay? I don't want to rehash it again with the video, but okay? Well, let's kind of back up a little bit and make sure that you've got a few things. I told you you didn't need to bother writing things down during the video, but there are a few things you do need to have written down. Okay? first of all, this formula is z equals x minus mu over sigma. That is a formula you need to know. That is in your IB formula book, but seriously, you're using it so much, okay, you ought to just know it by the time we're done here. All right, z is x minus mu over sigma. Now, how do we use this? Okay, let's find, with these 5 scores, let's find z-scores. Now, understand this. Each of these 5 scores is going to have a separate z-score. Okay? It's going to have a separate z-score. So, the first thing we need to do is find the mean and the standard deviation. Come on, go away. Alright? It's going to have a mean and standard deviation. So, let's find that first of all. What's the fastest way to find mean and standard deviation on your calculator? Okay, so stat, edit your list, punch in your values, 20, 18, 24, 26, 21, and then how do I find the mean and standard deviation?
Don't know one of those.
Come on, guys.
In list?
How do we do it?
How do you find it?
Do it on here.
He's trying
Guys,
to
this is something that we ought to know how to do by now.
mean and standard deviation, but
Okay.
to get it in the list.
Mean and standard deviation. You should know how to get stuff in a list by now as well.
No, I know how to get it in the list, but
Okay?
yeah. I thought you meant put mean and standard deviation of everything in list number 2.
No.
No, you have to go math, and then the second math.
Second math.
No, second stat.
Second stat.
Stat and then math.
No.
There we
And
go.
at the end, and then it's number 7.
Okay. Well, now hang on. One thing that you have to be aware of, and this is where you guys have to know your calculators. That standard deviation will give you a sample standard deviation, which is not what the formula that we use gives us. Okay?
So what do we do? We take
Now, you can see here we can find the mean using mean, but there's actually an easy way you can do mean and standard deviation all in one. And that is by hitting stat, go to calculate one variable statistics. Okay? One variable statistics, and we're going to use list 1. Okay? And now look at all this great stuff they give us. Okay? X bar is the same as mu, so I know our mean is 21.8. Okay? 21.8. Yes? In the spreadsheet, it's under the menu.
Minus.
I
I don't know how to do that. I was like, it's
Menu.
S step up is how you get to it.
If you do 4,
Well, you can do the stat calculation one variable statistics like
yeah,
that, but
and that'll give you everything.
And it-
So go 1, go the menu, and then statistics.
yeah, and
And
menu, and then menu 411 will get you to it.
Well, tell her what this are. Did you find it? Did you find one variable statistics?
Yeah, but you said number of lists.
Okay, so when you do that, you need to tell it that just to get the data from column A. Okay? So, number of lists, 1. Okay. And then your excellent list is just
stat count, one variable.
There you go. Okay. All right, so we have our mean of 21.8. Notice here, remember that notation that I was really picky about you guys learning? Like when you use an S versus a sigma, okay? Well, here what we want is this sigma x. That's our standard deviation. If you do STDEV, that function back in the list menu, it's going to give you this standard deviation, 3.19. That's not the one we want. We want 2.86 rounded to 2 decimals. Okay? So 2.86 is our standard deviation. Okay? So now, if I want to find the standard deviation, or I'm sorry, I have the standard deviation. If I want to find the z-score of each one of these, I need to do the following. I'm going to take each x, subtract the mean, 21.8, and then divide by my standard deviation, 2.86. Okay? So I have 20 minus 21.8 is negative 1.8 divided by 2.86, and I get a negative 0.629. Okay? Negative 0.629. Now, as you can see, this can be really tedious. Okay? So, what would probably be helpful to do?
Define a function for it.
Good, William. Do it with the entire list instead of with each score separately. So I'm going to do list 1 minus the mean, 21.8. And notice there are all the elements in the list. Okay? Then I'm going to divide the entire list by 2.86. And I get all my z-scores right there in the list. And you can scroll over to see. I already had the negative 0.629. Here's a negative 1.329. Next is 0.769. Next is 1.469. And then the last one, negative 0.280. Okay? Those are all our z-scores. Notice all the ones that are below the mean are negative. All the ones above the mean are positive. Now, how is this useful? I'm going to start with the positive values here, and we already looked at the standard normal table briefly, but let's take a look at, for the score 24, I have a z-score of 0.76. So what's the probability that a randomly chosen variable will be less than 24? Well, it's the same probability that the z-score for that score will be less than 0.76. Okay, so we come down here. Here's 0.7. Here's the 0.06. All right, so 0.76 is going to be this right here. Okay? So the probability here is 0.7764. That means this value of 24 is greater than 77.64% of all the rest of the data. Okay? So like if these were ages of people, in a certain population, this person would be older than 77.64% of all the rest of the people. Okay? Here for 26, okay? 26 is a z-score of 1.45. So here's 1.4, here's the 5. We come over here, and it's 0.9265. Okay? Yes?
You mentioned earlier the difference between the standard deviation of the population and the sample. What is the difference in the formula?
The difference, basically the difference in the formula is that for a population, you divide by n minus 1 instead of n. That's the only difference, but obviously it makes it a little different. Basically what it does is it makes it, your standard deviation for the population will always be a little bit bigger. And it's basically like we're allowing for variations in, or errors in our sample, or irregularities, I should say, in our sample. So the standard deviation is a little bigger. Yeah?
Like, was this table is always the numbers are greater? They're like greater than
What we're trying to find is this percent, the 0.9265, that's the percent that something with this z-score is bigger than. So 26 is bigger than 92.65% of all the rest of our data. It's always bigger than.
Okay, it's less than this.
Yeah. Now, the negatives, for the negatives, here's what you have to do, okay? What we're going to do for this one is to find the probability that a variable is less than a z-score of negative 0.62, we're going to take the complement, so 1 minus the probability that x is less than the absolute value of negative 0.62. In other words, look at the positive value. So here's 0.6, and here's the 0.02. So here's the percentage we're dealing with, 0.7324. But we're going to take the complement of that. So 1 minus 0.7324. Okay? So that'll be 672.2276. Okay? Does that make sense? And basically the idea that we're using here is that if we go to a positive 0.62, it's going to give us this percent. Negative 0.62 would have been equal to this part, the part above it. Okay, so we're using the symmetry of the normal distribution here to help us figure out these different values. So, negative 1.31, we go to 1.31, and we're going to do 1 minus the 0.9049. Okay, so we get 0.9951, or sorry, 0.0951. Okay, so pretty simple process. We are going to do a little bit more with these tomorrow, using the calculator and then using this. So you do not need to do the independent practice that's listed on the Sunday Post. We're going to do more with this, and we'll do the practice tomorrow. Okay? All right. Have a great day, guys.